Hey everyone, today we're going to start looking with section 8.1, and this is going to be chapter 8. There's a lot of the applications of the integral. So let's get started. We have a new chapter, so a new theme, and this time we have Star Wars. So if you don't know Star Wars, I don't know where you've been for the last 40 years, but it is started out at least as an epic space opera media franchise created starting with the 1977 Star Wars film and continuing on today. So if you don't know much about Star Wars, go ahead and read through there. But here it was where we start our calculus. The Star Wars franchise begins with Luke Skywalker, a desert farm boy orphan with aspirations of becoming a pilot like his biological father. When describing his abilities as a pilot, Luke says that he, quote, used to bullseye womp rats in my T-16 back home. They're not much bigger than 2 meters. Now, a T-16 is a skyhopper. A T-16 skyhopper is a high-performance air speeder with controls similar to the iconic X-Wing fighter that Luke would eventually pilot. So we can use this T-16 as an introduction to motion. So this is all about motion. Some things to remember is that the derivative of a position, remember we use s as position, is equal to velocity, and then the derivative again of velocity is equal to acceleration. And so with the fundamental theorem, we can work the other way around, where we have the integral of velocity is a change in position, and the integral of acceleration is a change in velocity. So more carefully reading, the integral of a velocity function dt is equal to the position at b minus the position at a. And we're all kind of familiar with how this works by now because we've taken integrals of all sorts of things. So here we have in our problem, Luke's T-16 travels with a velocity of t squared minus 8 over t plus 1 squared units per second along the x-axis. If the T-16 has position x0 at 9, what is the T-16's position at t equals 1 and then at t equals 5? So we're meant here to use the fundamental theorem of calculus and substitution method. So let's figure out our antiderivative first. So let's do the antiderivative. Let's say right about here. So we're going to find the antiderivative of t squared minus 8 over t plus 1 squared dt. Handwriting is looking pretty bad right now. Okay, we see two terms here. This first term here is pretty easy. That's 1/3 t cubed. But the second term is going to require a little bit more for us to do. So let's kind of rewrite that as 8t plus 1 to the negative 2 power dt. And use the u substitution here for this. Coming from where we just came from, you're probably thinking about using partial fractions here. But remember, partial fractions shouldn't be used unless you really need to. And secondly, there's no, well, yeah, unless you really need to, there's no reason to use partial fractions. And there's no reason to use partial fractions in this one, since the u substitution is pretty clean. So we got 1/3 t cubed minus 8 integral of u to the negative 2 power. dt is the same thing as du. So we got 1/3 of t cubed minus 8 multiplied by negative 1 multiplied by u to the negative 1 power plus my constant. All of that gets us 1/3 t cubed plus 8 over t plus 1 plus constant. Well, with our antiderivative out of the way, this definite integral becomes a whole lot easier because we can just substitute our antiderivative right into it substitute the upper and lower bounds. Notice that in the second one here, don't take for granted that this is always going to be 0. Note that even though this first term is 0, this second term is not going to be 0. All of that works out to a negative 11 over 3. The second one is going to be executed exactly the same way. First, we write down our antiderivative from 0 to 5. Then we substitute 5 and 0. I notice this should be actually a 5 here. And that works out to positive 35. All right. Now that we've looked at it that way, let's consider something else that could have happened, especially with our second problem. Now, if we had chosen to, we could have solved here for x5. And this equation, which I say falls out from the fundamental theorem of calculus, says that we can actually create a new equation for the position given an initial position and a displacement. So any position is equal to the initial position plus the integral from the old time to the new time of the velocity. Or another way, new position is equal to the initial position plus displacement. So you're going to have to kind of get familiar with seeing this integral here as a displacement. So displacement, of course, is equal to the new position minus the old position. And this right here is the integral, or not the integral, but the curve of the velocity. Over on the left side, we can see that the area is completely underneath the x-axis, and that makes us think that from 0 to, that looks like about 1.2, from 0 to about 1.2, we've got movement in the left direction. And then from 1.2 to 5, we have movement in the right direction. So here our displacement is negative, meaning we're moving to the left. And here our displacement is positive, meaning we're moving to the right. Of course, this is on the x-axis. If we're talking about the y-axis, then negative velocity means we're moving down. Positive velocity means we're moving up. Now, to get that exact coordinate, this isn't, we would have to solve the equation where the velocity is equal to 0, which would mean t squared minus 8 over t plus 1 squared is equal to 0. We would have to solve this, and frankly, this isn't the kind of equation that we will be solving in calculus. So the most expedient way of solving this would probably be either to use a solver on your calculator, or since I have Desmos here for me, I will just go ahead and click that. That looks like at 1.255. That's where we cross the x-axis. Coming back over here, we'll just write that. 1.255, that's where we begin, that's where we change from moving left to moving right. So on the interval from 0 to 5, Luke is moving to the left from 0 to 1.255 because the velocity is negative. And then we're moving from the right from 1.255 to t equals 5 because the velocity curve is above the axis. Moving on down, we have a little bit of describing something called total distance traveled. So total distance traveled takes all of the distance moved in one direction and the distance moved in the other direction and kind of puts it together. So let's pretend that if we move 5 feet to the left, and then we move 12 feet to the right, then our displacement would be a total of 17 feet. No, our displacement would be a total of 7 feet, because we would be 7 feet from where we started. But our total distance traveled, that would be that 17 feet. Okay, so total distance traveled, you just take all the distance to the left and all the distance to the right and add it together. Now, coming back to good old Luke on the T16, we see that he moves some distance to the left and he also moves some distance to the right. We calculated his displacement as 35 units. Now you notice here again, we're taking the integral from 0 to 5, and an integral is the displacement. So our displacement is 35. So how can we find displacement practically? What we can do, number one, is with a calculator at our disposal, we can, number one, just take the integral of the absolute value of our function. And that's pretty easy to do. Over on our calculator, we just push the math button over here, and we scroll over to the right, and we see abs, which is absolute value. And that puts those absolute value brackets. So we can build our function inside the absolute value brackets, push enter, and we will get our total displacement is 42.586, which is a little bit more than that 35 that was the displacement. So total distance traveled, 42.586, displacement 35. Now, if you don't have a calculator, you want to locate the values of the intervals of increase and decrease. Usually that means you set the velocity equal to 0. You integrate the velocity function for each of the identified intervals, and then you add the absolute value of all of those integrals together. Now we're going to go ahead and do this over here. Find Luke's displacement from 0 to 5. We actually already did that for part A. The displacement from 0 to 5, that's equal to the integral from 0 to 5 of the velocity, which we already found to be 35. And then the total distance is just the integral of the absolute value of that same velocity function. We already found that that's equal to 42.586, but to show you how to do this analytically, we would identify the intervals where we have positive and negative velocities, which we did earlier. That was from 0 to 1.255, we had negative velocity. And then from 1.255 to 5, we had positive velocity. Since this is positive velocity here on the second term, you don't technically need these absolute values because this will be positive already. And then now we just integrate all of these. Of course, we know what our antiderivatives are already. And then after we evaluate this, that's when you'll get your 42.586. So I don't envy this task because 1.255 is not a particularly easy number to work around, but it is possible. If you are going to do this analytically, chances are you would be getting a much easier integrand to work with. So that's it. This idea, the key ideas that we have here. We've got the idea that from the fundamental theorem of calculus, if we know that the derivative of f is f, then I guess I should say big F, the derivative of big F is little f, then we get this equation where big F at b minus big F at a plus the integral from a to b is little f. Now, in terms of something more concrete, as in the case of motion, we can see that position at B is equal to position at A plus the integral from A to B. And of course, this integral right here, we would just call that the displacement. So displacement is the integral from A to B of a velocity function, and total distance is the integral from A to B of the absolute value of a velocity function. Which brings us to our check your understanding. We've got a womp rat running with an initial velocity of 5 miles per hour, accelerating at a rate of A equals 2.4 miles per hour for 8 seconds. So the question is, how fast is the womp rat running after 8 seconds? We get a nice hint here that the integral of the acceleration function is velocity b minus velocity a. So let's take that hint and go for it. We've got the integral from a to b of 2.4 t dt equals velocity b minus velocity a. We see that we have an initial velocity of 5, so that tells me that a should probably be equal to 0. We want to know about after 8 seconds, so the integral from 0 to 8 of our acceleration function is the velocity at 8 minus the velocity at 0. The antiderivative is 1.2 t squared, so 1.2 t squared from 0 to 8 is equal to the velocity at 8 minus 5, which was my initial velocity. That integral works out to be 76.8. Move the 5 over, so 76.8 plus 5 is going to be the velocity at 8. Or after 8 seconds, the velocity is 81.8 miles per hour, and that is a very fast womp rat. So how far does a womp rat travel in those 8 seconds? This one I'm noticing a little bit of a typo here for our hint, but our hint should say the integral from a to b of the velocity is the position at b minus the position at a. I'll write that down again. Okay, so the integral of velocity is equal to the position at b minus the position at a, which is a problem because we don't have a velocity equation. But we have an acceleration equation, and we have an initial acceleration. So we can go ahead and try to build this velocity equation now. We just saw that if we maneuver our fundamental theorem of calculus, we can get that the velocity at t is going to be equal to the integral from 0 to t of a. Now normally this would be at dt, but since we have t in the upper limit, we've got to go to x instead. So the integral of ax dx plus the initial velocity. Substitute the equation for acceleration. Integrate, and then I've also substituted, we know the initial velocity was 5 from up here. And then after you evaluate this antiderivative, you get that the velocity of t is equal to 1.2 t squared plus 5. Moving forward to the velocity equations, we've got the integral from 0 to 8 of the velocity equation is equal to the position at 8 minus the position at 0, which seems like we have a little bit of a problem because we don't know the position at 8, nor do we know the position at 0. But the key is that this is equal to the displacement, and that's all we really want to know. We don't need to know position, we just need to know displacement, because that's how far the womp rat's going to travel in those 8 seconds. So we just need to integrate our velocity curve from 0 to 8. So we're going to integrate our velocity equation, substitute that in, find our antiderivative. substitute into our antiderivative, and then you realize that we've actually made a mistake because we are in units of miles per hour here, and our time is in seconds here. So let's start over again. Let's convert everything to the same unit. This first calculation looks okay because we have miles per hour per second as our unit of acceleration. So miles per hour per second. So it looks like the velocity is going to be 81.8 miles per hour. And we're still going to integrate the same way to find the velocity function. But now we're going to convert our 8 seconds to hours, and we get 1 over 450 hours. So when we find our displacement this time, we're going to integrate the absolute value of velocity from 0 to 1 over 450. Now, if you take a look at this, if you substitute 0 into the velocity function, you're going to get a positive result. And if you substitute 1 over 450, you're still going to get a positive result. So actually, to get the displacement, you don't need the absolute values here. So this is going to be equal to 0.4t cubed plus 5t evaluated from 0 to 1 over 450. That's going to be equal to 0.01111 miles. Multiply that by 5,280 and you get a total of 58.666 feet. So sorry about that little bit of a mistake on my part. I failed to read the units correctly, and of course it went up and it bit me. So be careful with your units, I guess, and good luck with this section. See you next time.